Okay, hello. This is the theory for chapter 4, which is constrained and relative motion. Right? So, relative motion, you've probably seen it on the formula sheet because it's just this. This is all there is to it. There's also this down here, but that's something else. Right now, we're only focused on this part of relative motion. So, let's begin with some definitions. Constrained motion is, I feel like it's obvious by the name, but it's when two things affect each other. So, for example, if we have a ramp like this, and we have a block on here, and it's connected to a pulley that's connected to this block. This is constrained motion because these two blocks, their motion depends on the other block. So for example, gravity is going to be pushing this block down. What happens is this block goes down. Well, intuitively, this block goes up, right? Or for example, this box is sliding down because there's not enough friction to keep it up, right? That means this block starts going up. Constrained, they're connected. So constrained motion is when the motion of a particle depends or affects the... Okay, I guess this will make sense English-wise. On the motion of another particle. All right? So that's pretty obvious. There will be... So when you're doing calculations, if we bring back our ramp here and whatever, you have this pulley block. You'll have to calculate velocity down of this, acceleration down of this, whatever. Position of this, we can call this block B, and we can call this block A. You'll do these calculations separately, right? So, and you'll set a datum. Like, for example, the datum would be, in this case, the center of the pulley. Just imagine the pulley's attached to something. There, so it's attached to this. There's your datum. So you have distance SB like this, and then distance SA like this, right? That's basically it. And then you'd have to like, you can break this into its components if need be. I remember there was a question on a practice midterm I did that was like this setup. Interesting question. It was pretty easy though, so that doesn't really matter. The positive direction is for constrained motion. Previously, we had like projectile motion and stuff. Like you had a cliff. You could choose this cliff face to be your datum, D for datum. And from here, you can choose up or down. You can choose which one's positive. For example, if you wanted down to be positive, you can choose down to be positive. In this case, you're going to set the direction towards the block as positive. So that basically means that your positive would look like this. This is positive. This is positive. This is what your positive would look like from this datum. That's about it. And now we're going to bring up an important equation for pulleys. And we're going to be making the assumption for a pulley that it's going to be constant length, right? Well, okay, that's not really an assumption. I feel like that's just something that's obvious. But it's going to be constant length. So you're going to have L, which means length of the pulley, and it stands for total length, is equal to... So there's this distance from the datum to A. So SA plus there's this distance from datum to B. So plus SB plus there's this bit of string or rope, whatever you want to call it, this bit of pulley, as you can see, that's above the datum. So we can just call that S1. Or you can call that whatever you want. You can also completely ignore it if you want to. Not right now though. That's for something else. Um, so this is our length equation, right? And this is all for constrained motion stuff. So pulleys are an example of constrained motion, and they're going to be like the main example of constrained motion. But if you think about it, right, length SA can change as this goes down and up. Length SB can change as this goes up and down. The length of the pulley doesn't change, and the length above the datum doesn't change either, right? So that means that L, and S1 are constants. So when you want to get the derivative, which is velocity, you're going to get 0 is equal to VA plus VB, right? There will be other factors that are part of this. You could get like something in the statement that says VA equals 3VB or something. You don't always start at the length equations and whatever, but this is just as we go through. This is what your velocity equation looks like, and in turn, that means that for your acceleration, it's 0 is A plus AB, right? Nice and easy. So, and by the way, when you flip your signs, it's basically one of these is going to become negative based on like this concept here. One of these is going to be negative. You can call if we put VB to this side, negative VB equals VA. So that means negative with respect to the datum, which means that if VB is negative, you're going up. Velocity-wise, you're going up. Now, this might get a little confusing if you're used to up being positive all the time, right being positive all the time, but you need to keep track of your sign convention, you need to keep track of your directions, and you always need a datum. If you don't have one of those, you're not going to have fun, right? And this is an easy example, right? Let me show you what can be a not easy example. Ceiling, 1, 2, 3 ropes. Here's a pulley, like so. And then we have this, and then this wraps around another pulley that's connected to this block. You get the idea. Another pulley here, and then another pulley here like this, connected to a block, and then connected to the roof. This is 1, 2, 3 masses, and then 1, 2, 3, 4 pulleys with 1, 2, 3, 4, 5 lengths of rope. I mean, it's one total length, but there's 5 sections of rope. You ignore these like ceiling ropes, by the way. These don't actually like do anything. You ignore those. They don't contribute to the pulley. This is complex, right? If you wanted to extend it, you could say like this block is connected to a car. This circle is a car, and the car is going this way. And now our thing is more complex, because now that means that this string connected to the mass is going to triangle when it starts moving, right? Don't worry about that for now, though. Nothing that crazy will be happening. This is just like, yeah. If you add up, so you're going to want to like label things as well if it isn't already labeled. So this is block A, block B, block C. And then you want to look at your strings and a datum. So as you can see, you have 2 fixed pulleys, right, to the roof. This pulley is not fixed to the roof. So what you can do in terms of the datum is you could set it up here, right? But that just leaves you with like this constant area of rope. And also this distance of rope as well is constant in terms of like everything else. So you can actually use this lower pulley as your datum. That makes it easier. You can like ignore all this stuff up here now. And you can have SA, 1 SB, another SB, 2 SC, and I'm just going to call this rope here. Oh, also you make the assumption that blocks that are connected to pulleys are just like where the pulley is. Like this is SA would be from datum to this line. SC is from datum to this line, because you're just assuming that the block is where the pulley is. I'm actually going to get rid of this car because this doesn't provide any benefits to this example. Anyways, yeah. So then when you're doing the length of the rope, so L, This is how I write lowercase l's. This is supposed to be a lowercase l. I made it capital because it looks not like an L when it's lowercase. Anyways, you get like L is equal to SA plus 2SB, 2SB plus there's 2 SCs, right? And there you go, that's your length. And then you would do the derivative for velocity, derivative for whatever, acceleration. And that is it, right? So pretty simple stuff. So in a summary here, for solving a constrained motion question is first step is you want to identify what's fixed and what's moving. Fixed and moving, I'll call them particles for now because that's what we're assuming they are, but I guess bodies is another word that works. And then for 2, you want to set a datum, like we did here, this white line, datum. And then for 3, you're going to relate the positions using length, like this equation. We've related the positions using length. And then final step is derivatives. Derivatives, right? Nice and easy. That's all there is to it. And now we want to talk, we've talked about when the movement is dependent, so constrained, but we want to also think about relative motion. So I'm going to put a divider here. We're going to think about relative motion. And this is also pretty easy to know what it is, but it's basically motion relative to a different frame of reference. For example, you might have done this in high school, right? You have a river, and you have the water, and you have the boat. This is a boat, and you have the observer, which is the circle. Now, you would have calculated, like, what is the velocity of the boat that the observer sees? What does that mean? Velocity of the boat relative to the observer. Basically, what is the observer seeing? If the river is 2 meters and the boat is 5 meters per second, both are per second, then the observer sees the boat moving at 7 meters per second. It's an easy addition. The formula, I mean, you can see right here, it's literally just addition, right? So relative motion is particles moving with respect to a fixed axis or with like respect to another particle. So relative motion is motion with respect, WRT is with respect to, by the way, with respect to a fixed axis or other particle. All right, nice and easy. No need to worry about that definition. So I'm going to change up the example here just for visually. We have this. We have one particle here and one particle here. There you go. These are particles. They have XY coordinates. We'll call this one A and we'll call this one B. All right. We want, for example, the position, which is S of B with respect to A. So what does that mean in terms of actually writing it? B over A. That's what it looks. I'm going to write this one out because typing wise it doesn't look that nice. S B A. The position of B relative to A. That's what that means. The position of B relative to A with respect to A, however you'd like to say it, is equal to SB minus SA, right? If SB, let's say we're looking at the Y, and these are, let's say we're looking at the Y coordinates. This is 3, this is 5. What's the position of B with respect to A? Well, we can imagine an origin, or I mean an axis here, along A. What is this? What is this Y coordinate relative to this? 3 minus 5, negative 2, right? So basically, it's like datums again. That's why, yeah, it's like datums again. Except your things won't always be fixed, so you can't like say it's a datum, but that's like a way you can imagine it if you'd like, right? Anyways, these are vectors, by the way. Well, they don't have to be vectors, but they can be vectors. And then, again, same thing applies for velocity. So v b with respect to a is equal to v b minus va. And then same thing for acceleration, which is b over a equals a of b minus a of a, right? And that formula is here, just rearranged for no negative signs, right? Velocity of b is equal to the velocity of a plus the velocity of b with respect to a. Now, it's not always going to be a and b. That's just notation. It could be 1, it could be 2. It could be just like anything. The symbols don't matter. That's just notation. You don't need to worry about the symbols. These are all for rectangular coordinates, right? X and Y and Z as well, if you want that. So don't use this for like tangential and normal. We went over that in chapter 3. Don't use relative motion for tangential and normal. Unless I'm mixing up a concept, I'm like 99% sure that is okay. If it isn't, I'll clear it up in the problems video if I do a question related to that, right? I'm like 99% sure that this is completely fine. So don't do these in normal and tangential. If you can, I'll just fix my speaking error, brain error in the problems video. And that's actually it for this chapter. These chapters are all really short, honestly. I took longer on the intro chapter, so that's kind of funny. That's all for this video. We're gonna be doing the same stuff in terms of calculations. This is gonna be new when we do pulley questions, and I mean the rest is just gonna continue to be this, because this is all we know. So we've just unlocked another section of the formula sheet, which is what is circled, excluding these circular coordinates, cylindrical coordinates, because we don't care about that for now. Anyways, yeah, thank you for watching, and I hope this was good. Thank you. Bye.